In this lesson, we are going to talk about a method of proof called proof by induction. And when I was in algebra, it was my very favorite type of proof because I thought it was very structured and, well, algebraic. But first, I need to caution you, just because you recognize a pattern doesn't mean you can jump to a conclusion and assume the pattern is going to work forever. That is not a logically valid method of proof, right? Because the pattern can switch right after, the last number you checked. Case in point, there is a super famous math blunder made by Fermat of Fermat's last theorem. He came up with this function that he thought would generate prime numbers, 2 raised to the 2 to the nth power plus 1. And he tried it for a couple, maybe 3 or 4 of them, and those were prime. And so then he just said, hey, it's going to generate prime numbers. Woohoo, I have a prime number generator. If you actually try to evaluate these function values, they get really huge very quickly. So if you're trying to test if a number is prime pre-calculator days, like not only did you have to calculate this value, but then you had to test to make sure it wasn't divisible by anything other than 1. And so he kind of stopped and said, hey, I have a prime generator, woohoo. Well, someone who's a little more diligent in their calculations and a little more patient, Euler, showed that at the function value of 5, you get this huge disgusting number that he showed was composite, thus shaming Fermat, right? So you don't just assume that a pattern works. That's not a method of proof. So in order to prove something very patterny or formulaic like this, you need a way to do it, and mathematical induction is the way to do so. Now, I always thought mathematical induction was kind of like a chain reaction, sort of like the dominoes that have been set up perfectly, so that when you hit one domino, pew, it'll cause the other domino, pew, to hit the next domino and make it fall. Well, mathematical induction works that way. So here's the actual principle of mathematical induction in all mathy language. It says, let P of n be some statement involving a positive integer n, like Fermat's formula. And the concept of induction is, if P sub 1 is true, so the very first value of n is true, for every positive integer k, the truth of pk implies the truth of pk plus 1. So you're saying that I'm basically going to assume that it's true for k, but if I show that it's true for k plus 1, that means it's going to be true for everything. So once I have this first thing set up, and I can show that the next one's going to be true, then everything after that's going to be true. Because this thing here is going to prove that piece of 2, piece of 3, piece of 4, piece of 5, piece of 10 million, whatever, is going to be true. Right? And that's the principle of mathematical induction. Okay? Because if you can get these two things, then you can show that it's true for all things. So in essence, it's like a chain reaction. Show it's true for 1. Assume it's true for some k. Show that it's true for the very next one, and then you have them all proven. So of course, I'm going to give you an example of a proof by mathematical induction. So now let's use the concept of mathematical induction to prove a formula for a sum. Now, you may have noticed I have this series here, 1 plus 3 plus 5 plus ... plus 2n minus 1. You might recognize these as the odd numbers. And this sum formula tells you that the sum of the first n odd numbers is just n squared. And so in order to prove this, I'm going to use mathematical induction. Now, induction has a very set way that things have to be done. And the first thing you have to do is you have to show it's true for 1. Which in this case, these are usually trivial. Showing it's true for 1 is usually trivial. So the sum of the first term is, well, 1. And then I use my formula that says that it's just the number of terms squared. And that's true. So yay, I've taken care of the first part of induction. Now, if this were not true, then you have a bad formula and you've proven that it doesn't work. All right. Now, the second part of induction is also very set. You have to do this. You have to assume it's true for some k. And you actually have to write that down like this is part of your proof. Assume it's true for some k. And so therefore, you are making the assumption that this thing here is true. So I assume that this is true. I'm going to be working with this concept. 2 times the k minus 1 is equal to k squared. And I just wrote it a little bit differently. I didn't put parentheses around the whole thing. And you'll see why in a second. Now here's where the algebra-y part comes in, right? This is where I need to show that it's true for the very next term. So I have to write out the sequence with the very next term added on. So the series, the k plus 1 partial term, is going to be 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. And I just dropped the parentheses. And then plus the very next term. So this is the kth term, but I'm looking for the k plus 1 partial sum, which means I need to write the next term. And the next term is going to be 2 times k plus 1 minus 1. It's the very next term, right? Now, this is where the algebra comes in, because I know that this thing here is s sub k, right? And then I'm going to just distribute here 2k plus 2 minus 1, which is 2k plus 1. And so then I can just add on the next term, which is just going to be 2k plus 1. So I have s of k, which was the first bits, and I'm adding on the very next term, which is going to be 2k plus 1. Now, I have assumed that s sub k is going to equal k squared, so I'm going to do a substitution, right? And if I factor this, I get k plus 1 quantity squared. And actually, now I'm done. Because if you think about what this formula says, it says I'm supposed to square the number of the terms. Well, right here I have k plus 1 terms, right? And what do I have here? I have k plus 1 squared. So I have shown that the k plus 1th term is indeed going to be the square, and therefore my proof is done. Now, one thing that I found helpful when I had to prove by induction was to think about what my end result was supposed to look like. So if I assume it's true for k, and I need to show it's true for k plus 1, then I would take this formula, or the original formula, the n squared, and I would insert the k plus 1 just to see what it was supposed to look like, because that would help guide me in figuring out the steps necessary to get that answer. So now let's do this other example of proof by induction. It's going to be a little bit different. It's going to have a little more reasoning to it than just algebraic manipulation. So let's prove that 3 is a factor of 4 to the n minus 1 for all positive integers n. Now remember, to start off a proof by induction, you have to show that it's true for the first term. So we're looking at if n were to equal 1, well, 4 to the first power minus 1 is 4 minus 1, which is 3. And 3 is a factor of 3, so yay, I have shown it for the first one. Now, remember, for part 2, we're going to assume that 3 is a factor of 4 to the k minus 1. So now let's look at what 4 to the k plus 1 is going to look like. So I have 4 to the k plus 1 minus 1, and I want to show that this thing has a factor of 3 in it. And here's a little trick. I am going to do a little bit of clever math magic here, and I am going to add on 0, but I'm going to show 0 in the form of negative 4k plus 4k. So I just added 0 to it, but in a format that I can actually use, because if you think about what this is, this thing has a factor of 3. And so if I can show that that thing there has a factor of 3, then this entire thing has a factor of 3. And I can do that by factoring out 4 to the k, because my exponent rule, say if I factor out a 4 to the k here, I get a 4 and then a minus 1, which is, oh hey, 3. So this also has a factor of 3. And so I'm adding two factors of 3, therefore 3 is a factor of 4 to the k plus 1 minus 1. Check.